All right, so we have some modulated signal, and it is a frequency hop signal, and we don't know a whole lot more about it other than that there's obviously something in the low frequency range, and it looks like maybe there's a second harmonic. So let's go ahead and take a look at that signal. We'll do a peak search to find the approximate frequency. Okay, so it's around 2.4 gigahertz or so. So let's go ahead and set the center frequency to 2.4 gig and see what's there. Okay, so now we can see some signal around 2.4 gig. It looks like the spectrum is moving to the left and the right, so that's maybe indicative of a frequency hopped signal. And it looks like there's maybe something else up here. Maybe that's a second harmonic or so. So let's just take a look at the fundamental for now. Let's go ahead and drop our span down to, we have 480 meg per division here. Probably some fraction of a division, maybe 200 megahertz span would be enough to look at that signal. All right, so we see the signal is jumping around in frequency over time. Let's go and do a max hold. So we'll go to trace config. We'll add a max hold trace here. Okay, and so we can see it looks like there's 3 channels down below and 1 channel at the top. And whenever we have modulated signals, we could use the positive peak detector, but the RMS detector is probably a little bit better choice for a modulated signal. So we can change that trace detector type to RMS. There we go. So let's take a look at what that looks like in the Demod spectrum. So we can open up Analog Demod. And there's a few more windows we could open up. We could look at the RF spectrum just to make sure that we're analyzing the full signal. We could take a look at the RF time domain, and that's going to basically show us the amplitude versus time. And we have the FM time domain. All right, and that should be sufficient for now. I'm going to just move the results summary over here so the FM and RF time domain graphs are lined up. Give a little bit more room to the time domain view since that's really what we're interested in. There we go. Now let's increase our demodulation bandwidth to be able to cover these signals. Now is maybe 160 megahertz would be the bare minimum we'd want here. 200 megahertz would definitely be enough to cover all of them. We'll change the RF spectrum here to be full span. And now we can see the 3 channels on the bottom and the 1 channel on the top. We'll increase our acquisition time so that we can cover each of these channels, hopefully all within a single acquisition. So let's increase that to 10 milliseconds. Okay, so now we can see these channels are changing in power a little bit, and that may just be a function of some of these channels being repeated in time, and sometimes they're represented 2 or more times in this 10 millisecond capture, and sometimes they're only represented once. All right, so the RF spectrum we're pretty much done with that. Let's take a look at the RF time domain. We can see that the power level drops below minus 40 dBm for some brief interval. It looks like it's around 100 microseconds or so. So we can trigger on that signal. Let's do an IF power trigger and let that trigger threshold be negative 20 dBm, negative 30 dBm, maybe even negative 40 dBm would be sufficient. Looks like that's just a little bit too low here, so we'll go to negative 30 dBm. Okay. And since we do have access to this trigger from our generator, we could also use that external trigger, but I think the IF power trigger is going to be a little more powerful for unknown signal that's radiated. All right, so now on the FM time domain, we'll look at that vertical scale, and it obviously is deviating more than plus minus 250 kilohertz, so let's change the scale on that. So let's take a look at least 20 meg per division, maybe more than that. Let's do 40 meg per division. All right, so when the signal cuts out, we notice the deviation goes plus minus 160 megahertz, and that's based on the demod bandwidth here, because the signal is really just noise at that point. So we can enable the squelch in this demod application, and that should take care of that. So let's go to measurement config, demod, and we'll turn on that squelch. We'll squelch signals below, say, negative 35 dBm. And what this means is we're going to let the FM time domain value be 0 hertz whenever the signal falls below that squelch point. All right, so now we see, let's do run single here. We can see some signal is occupying between, say, negative 80 and positive 20 megahertz or so. That's a really wide range, and obviously it's a lot more than what we want. So we probably need to add some type of low-pass filter to filter down that signal. So we will go to our demod config, go to the AF filter, and we could add 5% demod bandwidth filter here. Likewise, we could do the same on the RF time domain. Okay. And the RF time domain is not going to allow that, since that is not an AF time domain, that is an RF time domain. Okay, so that's helped. This is also using the auto peak detector. So really we care about kind of the average frequency within each frame of the signal, within each burst. So let's change this detector type from auto peak to average. And now we can clearly see we have some signal that is a little bit above. That's and multiple states here. Likewise, we could do the same on the RF time domain view. Go to auto peak, trace, RMS, and even drag that down too to see the peak value. You can increase that reference level as well, just to avoid compressing. All right, so what do we see here? We see something at negative 50 megahertz, and then maybe negative 30 megahertz, and then negative 70 megahertz, and negative 30 megahertz again, and then up here at about plus 70 megahertz. And then it looks like that pattern repeats. Let's go ahead and change the scale on that and do 20 meg per division. And these actually happen to be Wi-Fi channels that are 20 megahertz wide, and that's why they're separated by 20 megahertz apart. And we can see there's a little bit of frequency change as we go from the header of that Wi-Fi signal to the payload portion of that signal. So this is just a cursory look using the analog demod application. There's no automatic detection of each of these sections, although it's pretty easy to inspect that visually. So let's go into maybe a little more in-depth calculation. Let's use the transient analysis application. We'll center that at 2.4 gigahertz. And we're going to change our data acquisition. We're just going to look at central 160 megahertz around that 2.4 gigahertz carrier. We'll increase our measurement time to be able to see multiple of these frames, so maybe 10 milliseconds. And that's going to be the raw data acquisition. And then we're going to make sure that the analysis is going to include 100% of that acquisition. So let's go to link the analysis region to the full data acquisition, both in bandwidth and in time. Visually, what that looks like is shown here. We have measurement bandwidth and measurement time. We have some offsets if we wanted to specify that, but we're using 100% here, so the offsets aren't really relevant. All right, so we have some similar graph here that we had from the analog demod before, the region FM time domain. We need to make a few similar changes to that as well. We'll get to that in a little bit. But first, let's go ahead and configure what we're going to define as one channel versus the next channel. How far does the signal need to deviate, either in time or in frequency, in order for it to be considered a hopped signal to the next channel. So let's go to the signal description. And first we're going to specify what it means to be hopped in frequency. So we're going to go into manual mode, start frequency of 0 Hertz. These channels are spaced 20 megahertz apart, and we have a total of 8 channels, linearly spaced, even though we are not occupying all 8 of those channels. We'll replace the table from before. Each channel is 20 megahertz wide, so let's go ahead and let that tolerance. A modulated signal can exist anywhere within the 20 megahertz centered on that channel and still be considered part of the same channel, part of the same hop before it would be considered a new hop. So that's 20 megahertz. We'll apply that to this table. And then we need to shift everything down because this is all relative to the center frequency. Shift everything down by negative 70 megahertz. So we'll apply that to the table as well. So now we can see channel 0 is at negative 70 megahertz, channel 1 is at negative 50 megahertz, channel 2 is at negative 30 megahertz, and that last channel is at positive 70 megahertz. So let's go ahead and apply those settings. And now let's go ahead and define what it means to be a hop signal in time. So we know that a hop has to last somewhere on the order of about 1 millisecond based on the previous analysis. So let's do a little bit below and a little bit above that 1 millisecond, so 900 microseconds and 1100 microseconds should be sufficient to define how long that hop can last. All right, so now we just need to set the video bandwidth, effectively doing that filtering on this data with the average detector and the low pass bandwidth. This is basically separating the idea of intra-channel frequency hopping, which is the modulation, and we do not care about that in terms of hopping. We really care about the slow changes as it goes from one channel to the next. So on the region FM time domain, we'll enable the FM video bandwidth. And we could use 5% as we used before. We could also go down to 1%. That may smooth this trace up a little bit more. Let's go ahead and leave 5% just so it's the same as the analog demod channel. And it's using the auto peak detector here. And if I do a run single, we'll note that it's now found 9 hops in this acquisition. And there's a little bit of a 10th hop on here, which is shorter than the minimum 900 microsecond that we allowed, so it's going to ignore that. So let's change the detector type here. We'll go to trace config. We'll change that from auto peak to average. And we can also enable the average detector on the FM deviation time domain graph. Change that to average. And then on the spectrogram, we can change this from using the maximum detector to the RMS detector, since this is a modulated signal. All right, if we do run single one more time, here we see the full RF spectrum from frame number 0. We could change what we're actually showing in this graph from the full capture to just some analysis region. We could also change that to a hop. Let's just leave that at full capture for now. On the full spectrogram, if we double click the color bar, we can change the mapping of that color bar, and this helps us weed out some of that noise. So right around there is probably good. Okay, so now we can very clearly see some signal where there's these horizontal bars that tells us the beginning of a new acquisition, and so there's a little bit of blind time between these two acquisitions. So let's just look at everything above this first gray bar. So we have the remainder operating at, let's call this channel 3, and then it hops to channel 1, then to channel 2, then to channel 8, then to channel 2, and back to channel 3, and then it resumes to channel 1, 3, 8, and 2, and that pattern repeats. So this is a helpful view. Let's see if we can actually trend that over time. So we've automatically detected those hops here, and then if we zoom in on just the blue area here, the region FM time domain, this is going to show the deviation from the average frequency, and that average frequency is calculated as the 75%, the central 75% time of that, and we'll average out that frequency, and then subtract the local frequency from that average to figure out the deviation from the effective average of that. You can see here we have a positive 1.5 megahertz or so deviation, and then signal averages down to about 0 or so with a little bit of noise. And that's just because this is a modulated signal. Okay, so we can see then in the table let's maximize that we identified a total of 9 hops, and the state index said it went from channel 0 to 2 to 7 to 1 to 2, and then it repeated 0, 2, 7, 1, and so on. And then we have the beginning time of each of those. The dwell time on each of those was between the 900 microsecond and 1100 microsecond. In fact, it calculated that as 937 microseconds. And there's a 0.1 millisecond or 100 microsecond time gap from one hop to the next, and that corresponds with the idle time configured in this Wi-Fi hopping scenario. And then we can see the effective frequency that we've told the analyzer. This is the measured frequency, and so we can see there's actually about a 2 kilohertz shift in, or a 2 megahertz shift in that data. The deviation column tells us what the deviation is relative to the previous channel that it was at. You can see how much it jumped by. Or sorry, that the relative frequency column tells us how much it jumped from the previous. The hop deviation tells us how much the signal deviated within the hop. We have a whole bunch of other parameters here. So let's go ahead and add a trend plot. We'll do a parameter trend. Now we can see that it went from channel 0 to channel 2 to channel 7 to channel 1, channel 2, and then it repeated 0, 2, 7, 1, and so on. We can trend a whole bunch of other parameters as well. So we can change the x-axis. This is just on the x-axis showing us the time that hop began. And then on the y-axis right now we're choosing the state index, but we could choose the nominal frequency instead. That's pretty much the same thing, but just showing us in megahertz what that is. We could change this to measure the deviation. We can see that some hops are deviating more or less than others. We can measure the power. There's a bunch of other parameters here as well. We could also change that x-axis to be pretty much anything else. So anything that we see in here, we could export to our scripts, and this is automatically detected. This has done a little bit more analysis than what the analog demodulation application was able to do for us, where it just gave us a graph but we've actually automatically identified some of these hops. We also see a full spectrogram too, so if we see that not only is there a signal here, but maybe there's a weaker signal over here, we would have been able to measure that in the transient analysis application, whereas the DMOD is really only going to be the peak detector version of this, and it's just going to tell us the peak power at one frequency at a moment in time. We can change which hop we analyze. So we're going to analyze one hop at a time, and then within that hop, we can zoom in or zoom out. So we could pan around. This is going to auto scale the vertical axis if needed. We can zoom in at the very beginning of that. We get it zoom all the way out and show the analysis region. So this is effectively the same as this graph here, except this is showing the gross frequency of each of the hops. This one has taken out that gross frequency, so it's just the deviation relative to the nominal within each. So we can see how much each channel is deviating by. The height that we see here, this is using that auto peak detector, is not really telling us that we have a plus minus 5 megahertz or a 10 megahertz wide channel. That's actually a result of the 5% video bandwidth that we use. It's 5% of that 160 meg. So we probably would need to change this from the auto peak detector to the average detector, and then that lines up a little bit more with what we want. So this is probably a pretty good view showing us for each channel. It's removed the frequency hopping portion and shown us a little bit about what's in each channel. All right, so now let's go ahead and demodulate one of these channels. So let's open up the Wi-Fi channel, because we happen to know this is a wireless B transmission. If we didn't know that, then we'd have to figure that out via trial and error. The center frequency is currently set to 2.4 gig. So let's change this to 200 or 2330 meg. This is the lowest channel. And we want to increase the capture time to 10 milliseconds so we can capture at least one of those frames. And then we need to change the standard from wireless A to wireless B, which is what this happens to be. And when we change that, it reset the capture time. So let's set that back to 10 milliseconds. And here it's able to see the transmit channel with a 1.6% peak EVM, and then it's ignoring all of the channels that fail outside of that bandwidth. All right, so that's a cursory look at this frequency hopped signal using the FSW, using the spectrum analyzer application, the analog demod application, the transient analysis hop measurement application, and the Wi-Fi demodulation application. Thanks for watching.